Hi everyone, I'm Herman and I'm a PhD student at Department of Computer Science and Engineering. So it's my honor to be invited at this symposium. So today I will be talking about towards automatic instrumentation by learning to separate parts in symbolic multitrack music. And I'm currently jointly advised by Professor Julia McCauley and Professor Taylor Kirkpatrick. So before I get started into my research, I would like to talk a bit about myself. So I do music cross AI research. And so now I'm a PhD student at UC San Diego. And previously I interned at Adobe and Yamaha. And I also work as a research assistant at Academia Sinica in Taiwan. So in this work, we are interested in the task of automatic instrumentation. So by definition, we define this task as dynamically assign instruments to notes in solo music. So there are two particular use cases. So firstly, most modern keyboards actually have a functionality called zoning. So in zoning, a musician can like assign different zones on the keyboards to different instruments, and when the musician play on that keyboard, then it will sound like you are playing multiple instruments based on the zones you play. And there is also another use case is in composing. So a typical way how composer work is that they would try to compose something on guitar or on piano and then try to arrange it into another ensembles. So the task of automatic instrumentation could be used for in this case that you can transform a solo music into a different ensemble, basically. Yeah, so here's an overview of the whole project. So firstly, we want to get data for solo music and its instrumentation, which is hard to get, but fortunately, we have lots of multi-track data set. So we acquire pair data of solo music and its instrumentation by downmixing the multi-tracks into single track mixtures. So now we have the mixture and the multi-track. And so we try to train a part separation model that learn to infer the part label for each note in the mixture. And then we can produce the multi-track. So this way we approach automatic instrumentation by treating input from a keyboard player as the downmix mixture, and then we separate out the relevant parts to get the final multi-track output. So in this study, we consider 4 datasets of diverse genres and ensembles, and they are Bach chorales, string quartets, GAM music, and pop music. So as you can see, they differ in the hours. So the pop music has is the largest and the most difficult one. And they also have like different ensembles. So the models we use are that we propose are deep sequential models, including online LSTM and offline by LSTM. So the online LSTM means that the LSTM doesn't have access to future information. On the other hand, offline by LSTM can have the future information, and that will be useful in the composing case where you get to know all the past and future information. And we also consider 3 baseline models, which are zone-based algorithm, closest pitch algorithm, and also a multi-layer perceptron from previous work. So, and here are the input features. So basically we have time, pitch, duration for each note, and we also have the frequency of that particular pitch, and we also have the timing information of beat and position. So with all this, firstly we show some qualitative results. So as you can see, we have Bach chorales, GAM music, string quartets, and pop music. So basically, the models achieve very high accuracy, and the examples we show here are all hard cases. So as you can see, like for Baccarat, it's hardly making any arrows, but in this case, there's an arrow in the baseline. And so like this string quartet, it's a particular difficult one that you can see the model makes some mistakes here. And so here are some quantitative results. So as you can see in this table that our proposed LSTM and bi-LSTM models outperform various different baseline models. And we also have bi-LSTM outperforms LSTM, which is obvious because bi-LSTM have access to future information, while LSTM only access to the past information. And also we found that like LSTM models outperform their transformer counterparts. Okay, so here is a demo. So first we listen to the original instrumentation of a song. So now we remove all the instrumentation information and then try to use our model to generate like instrumentation this particular song. Here's the result. Yeah, so as you can hear and also seen from the visualization here, basically the model get right at all the baseline and also get to correctly assign different instruments to the long notes and also like the higher notes. And here's another model that bi-LSTM, which has access to future information, and also we have the entry hints that the model knows exactly when each track start to play. So here's the result. Yeah, so as you can hear that the model correctly like differentiate different instrument based on their characteristic and assign like different group of notes for different instruments. So that's basically what we expect in the instrumentation, like automatic instrumentation. Okay, so to sum up, we propose a new task of path separation, and we show that our proposed models outperform various baselines. And finally, we presented a promising result for applying a path separation model to automatic instrumentation by basically downmixing the mixture, by downmixing the multitrack into mixture and then try to recover the part information. So there are several future directions. First, we would like to try generative modeling of automatic instrumentation because it's basically a one-to-many mapping. And we also want to try unpaired automatic instrumentation and large-scale pre-training for symbolic music models. So I would like to thank the J. Young Foundation for supporting my PhD study with the J. Young Fellowship. Yeah, so thank you.